This video is on equivalence and validity involving quantifiers for discrete math. So what is equivalence? Two statements are equivalent when, no matter what values, true or false, you give each of the statements, you get the same value, true or false, back from each of the statements. So in other words, in terms of truth tables, the end result of their truth tables are the same. When dealing with equivalency and quantifiers, there are a few rules that you are going to need to remember. The first rule is this one that's on the slide right now. In the parentheses, you'll note that there is just one predicate, q of x, and then there's p, where p is just an arbitrary true or false value. And so the only thing in parentheses that's within the scope of the quantifier is the predicate, q of x. That's really important because what it means is we can distribute the quantifier into the conditional. So it just so happens that when the premise is the predicate, that when we distribute the quantifier in, we have to flip the sign. So in this case, it becomes existential. So in this one, we just flipped the insides. The premise is now the conclusion, and so forth. When the predicate is in the conclusion and you distribute the quantifier, you don't have to change it, so that's nice. And then it's similar for the existential quantifier. Again, when your premise is the predicate and you distribute, then you just flip the sign, or the quantifier sign or symbol, whatever you want to call it. And then when you have the conclusion as your predicate, you don't change it. This set of 4 rules uses a concept known as null quantification. Now there are 2 more rules that you're going to want to remember when dealing with quantifiers and equivalency. And the first one is that if you're given something with a universal quantifier and just what's within parentheses is just a conjunction, then you can distribute through. However, you cannot distribute through a disjunction unless, of course, you are using existential quantifiers, and then you can distribute over a disjunction, however, not a conjunction, like the universal quantifier. One way to make sense of these is to think of them in terms of what they mean, just translate them in words and then think of them like that. But I find that at least my brain is not very good at doing that. So what I'm going to do is I'm going to use truth tables and show you that the first rule here is indeed equivalent. And you can do the same process for the rest of the rules if you don't believe me and you want to convince yourself of their equivalency. Or, again, you can think of it in your head, but I think that's probably too confusing for me. So the first part we're going to prove is the left-hand side, or we're going to drive the truth table for the left-hand side. When dealing with quantifiers, you want to get rid of the quantifier and any conditionals because that just makes it more confusing, more likely for you to mess up. So we convert the q of x then p to not q of x or p, and then we string these not q of x or p together with the and symbol, so a conjunction. And it's just a bunch of conjunctions. That's what a universal quantifier is. So let's fill out the column for not q of x or p. Look, not q of x is false, p is true, so false or true, that's true. True or true is true, false or false is, of course, false, and true or false is true. Okay, so we've done the parentheses part. Now we just need to do the big long conjunction, and what that is just the left-hand side written in a different way without the conditional or the quantifier. So we look at the column we just did and we go, okay, so this would be true or true and true and true and true, and that of course is true, and same thing here, false and false and false and false is false, true and true and true and true is true. Okay, so that is our left-hand side. We get true, true, false, true. Now, if everything goes accordingly, we should get that for the right-hand side. So, for the right-hand side, let's get rid of that existential quantifier right off the bat, and note that it's part of a conditional, so we're going to convert the conditional as well. So we get not q of x or q of x or q of x and so forth, and then we add the or p. We're going to use De Morgan's to just clean that up a little bit, and we get not q of x and not q of x and so forth and so forth, and then we have the or p, of course, from the conditional. Let's do the column and just worry about the not q of x and not q of x and so forth. So we have false and false and false and false, that's just false. True and true and true and so forth is true. We have false and true. So now all we have to do is add the p. So we look at the table, we go, okay, false or true, that's true. This is for the right hand side. And then we go true or true, that's true. False or false is false. True or false is true. Okay. And that is exactly what we got for our left-hand side. So we can conclude that they are indeed equivalent. So let's look at an example. This statement looks pretty long and complicated. It's got two quantifiers, two predicates, but what's important to note is the predicates within the parentheses are within two different scopes. They have two different domains, x and y. So they're not related, and we can use the null quantification rules. So let's go ahead and do that. And we have this, the left-hand side, we distributed the existential, it's in the conclusion, so we don't change it. The other one, we had to change the universal to existential because it's in the premise. And now we just do this for the remaining quantifiers, and we get this. It's interesting to see that they come out to be the same on either side. So no matter what value you give this statement for p of x and p of y, it's always going to be true then true or false then false, which means actually that this is a valid statement, which is what we're going to discuss next. So, validity. Anytime an implication is true, i.e. not true or false, or true then false, is what you can think of when you think of validity. The formal definition is the conclusion must follow from the premise. This might help to look at the truth table for a conditional. So, when the premise is true, the conclusion is true. Well, that makes sense. So that is valid. When the premise is true and the conclusion is false, that doesn't make any sense. I mean, the premise is true, then the conclusion has to be true. But it's not in this case, so it's not valid. And when your premise is false, by definition, we don't know what the conclusion is, so we say it is valid. It's just undetermined, so that is valid. Some examples: if a dog is an animal and a cat is an animal, that's true, then a dog is a cat. A dog is obviously not a cat, so that's true then false, which is not valid. If the temperature outside is greater than 32 degrees Fahrenheit, then the ice outside will melt. Okay, so if the temperature is greater than 32 degrees, that's true. Then the ice outside will melt. That's true. Okay, true then true is fine. If the temperature is less than 32, okay, so the premise is false, and it doesn't matter what the conclusion is. In this case, it's false, but it really doesn't matter. If the premise is false, then it's true. The important part to note is that it's never true then false, which means that this statement is valid. So that's this video, and I hope you are able to make more sense of validity and equivalence now. Thanks.